Okay, so we're good to go. As I've mentioned a couple times, this is the second of our 3 topics that we cover in calculus. Okay, this is differentiation, also known as taking a derivative. So today's lesson incorporates some algebra. It incorporates some conceptual stuff, but there's nothing really new here mechanically. And that doesn't make much sense, but you'll understand what I mean as we get through it. Okay? So we're going to talk about the difference between a tangent line and a secant line as part of our lesson today. Okay? So, like I said, tangents and secants, I'll refresh your memory on the difference between the two. And then we're going to start looking at the slope of a tangent line to a curve, which is, you just did that on the intro, but we didn't call it that. And then we're going to talk about the limit definition of derivatives. So there is similar to when we did continuity, there's a formal definition that we're going to talk about today. It's kind of a pain in the butt. And then what we're going to do is explore in days to come tricks that will save us a lot of hassles. Then we have to compare differentiability. That means being able to take the derivative, which at this point you don't really know what that means. Compare that with continuity and see when is a function differentiable. In other words, when can you take a derivative versus when is it continuous? I have lost the ability to speak on a Monday morning. And then you should be able to hold your breath for 45 seconds. Okay? Are you ready? No cheating, no breathing through your nose. Take a deep breath. 3, 2, 1, go. "30 seconds remaining." Is anybody actually holding their breath? Good. 20 seconds. Ten seconds. That's time. Who made it? Good. All right, so you've accomplished one of the objectives today. If you do nothing else today, at least some of you were able to hold your breath for 45 seconds. The calculus might go to hell in a handbasket, but as long as you could hold your breath for 45 seconds, you can check that box. Okay, so let's do a little bit of geometry / algebra. And we're going to talk about tangent line. So tangent line, you know this already, but we'll review it. A tangent line hits a function at exactly 1 point. Notice the notation there. We're switching from x and y. You should have done this in pre-calculus, but if you didn't, you'll get used to it now. We no longer refer to a point as x comma y. It's now x comma f of x. Okay. We'll slip back into old habits occasionally, but for the most part, this is going to be our new notation for a point on a curve. Okay. Secant line, however, is a line that hits a function in more than 1 point. It could be 2, it could be 6. Think about, for instance, taking a sine graph and drawing a horizontal line at 1/2. It would hit it in an infinite number of points. That would be considered a secant line. Where I'm pretty sure it's impossible to draw a tangent line to a sine graph, but we'll get to that later. Okay, so we got a little demo for you here. If I can get this to work. Okay, there we go. Yeah. Okay, here we go. So let me outline what's going on here so that you understand the problem. I've got this blue function. Okay, it happens to be, I'm pretty sure it's a cubic. What it is irrelevant. So I picked a point P over here on the left-hand side, and that point is at some random location, which we'll call X. And then I moved over to the right, and that got me the point Q. Okay. And Q is a certain distance to the right from P, and we call that distance delta x. So now you're going to start to see some things that you've used start coming into play. So for instance, if P is located at x, then Q would be located at x plus delta x. Okay. And because we're staying with that new format, the point P has a y value of f of x, because remember, we're no longer using y, we're using f of x, which makes the y value of Q up at f of x plus delta x. F of x plus delta x, where have we seen that before? Yeah. Okay. Everybody good with this? I haven't talked about this red line yet. We'll get to that later. But I've got this green line, which is a secant line. It actually hits the graph, in this case, in 3 places. Okay. Everybody understand the scenario? I'll give you another second to take a look at that. Okay, good. So please calculate the slope of the green line. Okay, we good? y2 minus y1 over x2 minus x1 gives us the slope of that green line. Okay, so that would be f of x plus delta x, the y value of Q, minus the y value of P over the x value of Q minus the x value of P. Okay, and that's the slope. Ooh. F of x plus delta x minus f of x all over delta x. Well, that looks familiar, doesn't it? Yes? And I'm sure that's what you got for an answer, right? Good. Now, oh, we did, okay, I forgot I did it. Okay, there it is, great. Slope of the secant line, okay, from that pretty picture. Well, that's not very exciting. It's just it's an Algebra 1 problem with some x's and delta x's thrown in there just to make things interesting. But again, this should look pretty familiar because we've been practicing with that for a while, also known as the difference quotient. So how do we incorporate some calculus into this? Okay. Well, what happens, as the question says, Q slides towards P. So let's go back to here. Where's my thingy-majobber? Stop it. Hold on, we're having some issues. Experiencing technical difficulties, please stand by. Oh, that's why. Okay, so this puppy's back now. So what happens when Q slides closer to P? Notice x is not changing, f of x is not changing, but delta x is changing, and f of x plus delta x is changing. Let me stop there for a second. Tell me how delta x is changing when you watch that thing move. What's happening? How small? Well, let's keep going then. Hold on. Before you answer that question, let's let this thing finish. Sometime before I die. How about those bears, kids, huh? Almost. That took a lot longer than I figured. Boom. What happened to delta x?
It's 0.
Yeah, what do we call that in calculus? What do we call that when delta x goes to 0? This is awkward.
Would it just be a point?
Nope. Bella, pick a letter. Sorry, I got you with a mouthful.
O.
Oh, no. John, pick a number. Or sorry, pick a letter. Pick a number.
Y.
Why? Kevin, pick a number. Sorry, I keep saying that. Pick a letter. Kev? We can't hear you. You're not muted. Still can't hear you. He's experiencing technical difficulties. Prasan, pick a letter.
E.
E as in elephant?
Yep.
That's a good choice, but not right. Christian?
I.
I, good call. Cindy?
S.
S as in salamander?
Yeah.
Uh-oh. Bethany?
T.
T is a good call. Good. Keep going, Bethany.
I have no idea. D.
D as in donkey. Oh, one guess left. Amanda?
M.
M. Keep going, Amanda.
L.
L. It's a limit. Calculus concept. What happens when delta x gets very small? What value does it approach? Regardless of what value it approaches, we're still looking at a limit here. We did that already. So, delta x is approaching 0. We're sliding that point Q over until it matches up with P. The gist of the exercise is that we're taking a secant line, which hits a graph in multiple spots, and reducing it to a tangent line where it hits in only one spot. Okay. So we get that. And you've done that before. We started doing the difference quotient early on. Initially, it was just an algebraic experience, a practice, plug and chug x plus delta x into the function, plug in an x. Then we took the limit. We weren't really sure why, other than that the fact that we were talking about limits. Little did you know that it's one of the more important topics that we will talk about in calculus. So the secant line has a nice plane slope. Without the limit, the secant line is just a y2 minus y1 over x2 minus x1. As soon as you take the limit of delta x approaching 0, it becomes the slope of the tangent line, which was the slope of that red line. Now, hopefully you understand how algebra doesn't help us here. Because it's a tangent line, it only has one point on the curve. And therefore, we can't do a traditional slope calculation of y2 minus y1 over x2 minus x1. So we have to come up with some other method, and that method we have is this limit equation. Okay. Depending on the function, you've done this enough to realize that if the function is nice and easy, this is an easy calculation. If the function is ugly, like for instance negative x squared plus 4x plus 3, like I did on the exploration, it gets a little nastier. Now imagine doing that for something like a quintic. That would be a 5th degree polynomial. That's going to get really ugly. Are we going to do that? No. We're going to cheat and find ways to get around that difficulty. Okay, so let's take this nice easy quadratic. Paige, what can you tell me about that quadratic? Anything helpful?
It's a parabola.
Keep going.
It hits the origins 0, 0, I think.
It does, yeah, yeah. Is-
it's facing up.
It's facing
Or
up.
opens up.
How many times does it hit the x-axis?
Just once.
It's
Twice.
a parabola. Yeah, it goes through the origin and then hits somewhere else. Okay, which is not relevant to what we're doing, but it'll come into play in a little bit. Okay, so we want to know the slope of the tangent line at 440. Now the problem is it's a tangent line, not a secant line, so I don't have 2 points. I can't calculate 2 points. Okay, and in fact, if you're a visual learner, you can pull out your Desmos and graph 3x squared minus 2x and see what it looks like. But at this point 440, it's going to have a tangent line. And we want to be able to calculate the slope of that tangent line. That slope of the tangent line is going to be found using that formula. Notice the slope of the tangent line. M is slope, which means you're going to have to plug into that monster. So go ahead and do that. These actually, you're going to do these in reverse order. You're going to end up with the slope of the equation for the slope, and well, no, just do it. Calculate the slope of that tangent line, please, using that quadratic. So you got to do some x plus delta x. You got to do a bunch of other stuff. Go ahead. I'll give you a couple of minutes to work on that. Marcus,
Yeah.
in this case, what's f of x plus delta x equal?
Wouldn't that just be 3x squared minus 2x, or
No, that would be f of x. What's f of x plus delta x?
3x squared minus 2x plus delta x.
Nope. You got this. What is this term? What does that mean? It means go to f of x, wherever you see an x, put it in x plus delta x.
Okay.
So what does that give me?
So it would be 3 x plus delta x squared minus 2 x plus delta x.
Oops. Perfect.
Okay.
You'll notice I put the brackets in there. I like the brackets so that we don't have any mistakes with minus signs. F of x is just 3x squared minus 2x. All of that over delta x. Okay, that's the easy part. The hard part now is simplifying this. The limit as delta x approaches 0 of 3x squared plus 6x delta x plus 3 delta x squared minus 2x minus 2 delta x minus 3x squared plus 2x, all of that over delta x. Boom, 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 boom. I'm running out of room here, but hopefully you see that what I'm going to end up with is... what am I doing? If I factor out a delta x out of all of this, I'm going to bring this up here. I get the limit as delta x approaches 0 of 6x plus 3 delta x minus 2. Oh, and the delta x would have gone away, so this goes away. All right. Which gives me a limit then of 6x minus 2. Now, this is going to bother people. It should bother you because this is a new experience. Everything you've done up until this point, when you calculate a slope, you get a numerical value. Oh yeah, that slope looks like it's about positive 4. That slope is negative 1/2. You get numerical values. Now, in this case, we're getting this bizarre equation for a slope. Well, how is that possible? Well, think about, you have a parabola, okay? And if you graphed it in Desmos, you understand. You have a parabola, and if I pick any point on that parabola, the tangent line is going to look a little bit different. Okay, so if we went to that picture that I had before, let me go back a little bit here. Where's my picture? Oh, this guy. Okay, if you look at me moving P to a different location, that tangent line is going to change. For instance, what if I put P right here?
So it would be 0.
The slope would be 0, correct. Okay. If I put P over here, I'd have a slope of negative, maybe negative 1, something like that. Where it is now, it has a positive slope. Up here, like I talked about, it's going to have a slope of 0, a negative slope, another slope of 0, a positive slope. When you put that point in different locations, it gives you different values. And that's why, in this problem, we get an equation for the slope. Well, it tells us we'd like to know the slope at 440. In other words, I'd like to know the slope when x is equal to 4. So that would give me 22. I think I did, yeah, I did my math correct. Okay. That's a pretty positive, large slope. So it's way over at 440 because it's a fast climbing parabola. If I picked a different location for this point, the slope would change. But again, we're allowed to do that. And that's why we get an equation. Can I erase this stuff at the bottom here? My calculations, yes or no? Yes? Okay. Because I need to do part B now. You've heard me say this 1,000 times. I'll say it 1,000 times more. What do we need for the equation of a line?
Point and slope.
Point and slope. Do I have a point?
Yes.
Do I have a slope?
Yes.
Done. Y minus 40 is equal to 22 times the quantity x minus 4. Easy peasy. If we were to pick a different point, it would obviously change our equation. It would also change the slope. Ben, where's the vertex of this puppy?
Of 3x squared minus 2x.
You got it.
It's negative b over 2a, so that would be
Okay, so
2 over
x
6.
negative.
No, it would be 2 over 6, and then you plug that back in, so...
So we know the x value is 1/3.
Yeah.
Okay.
Yes.
All right, fine. Ben, let's stay with you. What would you expect the slope to be then at when x is equal to 1/3? Don't overthink this.
Oh, wouldn't it just be... Would it be, like, 0 because it's just, like, sitting at the vertex, or...
Perfect. So a non-calculus answer would be 0 because it's that level point. It's the top of, or no, the bottom of the parabola. And so its tangent line would be 0. Perfect. Also, what happens when I plug 1/3 into that puppy? 1/3 times 6 is 2. 2 minus 2 is 0. Okay, good. So again, my point being, if you move it to different locations, you get different values. And that's, again, what's going to freak people out because you're always used to calculating a slope where you get a numerical value. And a lot of times that's not going to be the case. So let's, before anybody's brains melt, let's stop for a second and answer any questions that you have about the concept of what we're doing. Preguntas? Going once, going twice. Sold. Okay, so before we move on, let's take a 5-minute break. It is 10:23. I'll see you all back here ready to rock and roll at 10:28. Go! Get up, go do something. Sorry, I muted myself. Get up, go do something. All right, I got 28. Let's pick up where we left off. Everybody back? Good. So, quick public service announcement before we continue. Because I'm pretty much standing in my classroom talking to myself, because nobody ever says anything, if I'm going too fast, you need to let me know. Okay? So unmute yourself and say, hey, could you slow down? If I'm going too slow, unmute yourself and tell me to pick it up. More than likely, you're not going to tell me to pick it up, but if I am going too fast, please let me know. Okay, so this is a blue box, so it comes from the book. It's the fancy schmancy definition of what we've been doing. And so if we want to know the tangent at some point C, where they introduce this concept of the point C, we're going to get the limit of the slope, delta x, or delta y over delta x is a slope. And when you then calculate that slope, we're taking the limit of the secant line as it approaches, as delta x approaches 0. Okay, so slope of the tangent line. We're going to do this slope of the tangent line calculation ad nauseum. Okay, that's Latin. That means until you puke. Okay. We're going to spend a lot of time doing it. Okay. So, what happens when that tangent line to the curve doesn't have a slope? Okay, we get something like it says called a vertical tangent line. And so they come from these two things. If you do the slope calculation using the limit and you get infinity or negative infinity, then you have a vertical tangent line. Okay, so think about that visually. Don't get bogged down in the calculus. Think about it visually. So here's my example. Here's my picture. I've got this curve. If I start with this tangent line up here, I'm going to have some positive tangent slope, or some slope that's positive. As I move it down a little bit further, as it continues to slide, that tangent, the slope of that tangent is getting bigger and bigger and bigger. So then I bring it over here, and eventually, when it gets to that vertical point, it's going to have a slope of infinity. So we've said, vertical lines always have that slope that's undefined. Okay. Why? Because there's no change in the x value. The delta x on the bottom gives you 0, and we can't have zeros in denominators. But because this is calculus now, we can talk about limits as it gets very close to 0. And so depending on the direction that you come from, if you get infinity, like this slide says, if you get infinity or negative infinity, you're going to have a vertical tangent line. We won't see that a lot. We're going to be more concerned with some of the stuff that we already talked about, which is where the tangent line is equal to a numerical value, or even 0 is going to be a big thing for us. Verticals pop up every once in a while, but not that crucial. Okay. So this whole thing that we've done is called taking a derivative. I'm sure you've heard that term before. If you've had, how many people have already had physics? Raise your hand. How many people are currently in physics? So I'm sure this is not a new term for you, but it's called a derivative. The act of taking a derivative is called differentiation. Okay. And we have some new notation here. F prime of x is how that's set. And we're going to use a lot of terminology to mean the same thing. The derivative of a function. Same thing as the slope of the tangent line of a function. We've got some other stuff that we're going to talk about with this derivative later on. But for now, this is it. F prime of x. Okay, is that thing that we've had already, which is the limit function. Okay. Here are some different notations. All of these mean the same thing. We're going to use most of them. This gets to be a pain in the butt. I'll explain to you in a little bit why we have different notation. Why can't somebody just pick something and run with it? And I'll explain why in a second. F prime of x, dy dx. The derivative of y with respect to x is what that means. Y prime. So if we have the function written in y equals, you can take y prime. You've got the derivative of f of x with respect to x. And that with respect to x becomes very important because that's telling you what the variable is. Okay, we don't get into it very often, but there is something called multivariable calculus where you've got x's, z's, q's all wrapped up into one equation, and you've got to figure out which one is the variable. And then this last one, capital D, the derivative of y with respect to x, just different ways of writing it. I know this is very confusing. Again, why can't we just pick one and go with it? Talked about that already, and we've got that. Okay, so let's talk about why this happens. We're going to have a quick history lesson here. Okay, two guys. I don't know if you can hear that. Can you? Okay, good. I spent all that time putting it in there. I hope you can hear it. Isaac Newton. Give me a emoji thumbs up if you've heard of Isaac Newton. Of course, everybody's heard of Isaac Newton. Apple falls on his head, physics guy. But what you didn't know, supreme jerk. And I'll explain why in a couple minutes. On the right, Gottfried Leibniz. How many have heard of Leibniz? Nobody. There's a reason for this. Okay, so Newton and Leibniz, about the same time in history, both come up with calculus. The odds of this happening are astronomical, but it appears that it actually happened this way. That's why there's different notation. Newton used the F prime notation. Okay, so this business, this, I don't know why I'm pointing. You can't see where I'm pointing. This, let's try that again. That is Newton. As he's creating calculus, as he's discovering, I don't know if he created or discovered it, however you want to phrase it, he's using that notation. Leibniz uses this notation. And they start to figure out that they're doing the same thing. Okay? So, I think that sound's going to play again. All right, I can skip it. Good. Okay, so back then, this may come as a shock to you, but mathematicians were like rock stars. Everybody knew who Isaac Newton was. He created some math stuff. He was a cool guy. Nobody knew who Leibniz was. Isaac Newton found out about Leibniz, and he was pissed. How dare this guy do the same thing I'm doing? I'm Isaac Newton. I'm the apple on the head guy. I'm the physics guy. I'm the, I've done all these. At the time, he was the head chair of some international mathematics committee. This guy, Leibniz, he was nobody. Look at the hair on that guy. I mean, what are you going to do? How do you go out in public like that? So Newton decides, I can't have this happen. I'm going to ruin his life. And he did just that. He basically, he jumped on the Snapchat and Instagram, started dissing him. People started to believe him. Newton, everybody knows Newton. Leibniz, nobody knows Leibniz. They did the exact same thing, but because Newton had a better social media presence, everybody knows about Newton. No one knows about Leibniz. That is why we have different notations. Now, where did the other notations come from? I have no idea. But the two main ones that we're going to use, one's from Newton and one's from Leibniz. Okay. So, let's do this again. So now we're going to find the derivative. It's the exact same thing we've done before. We're just calling it something different. Okay. Now, notice it says, though, finding the limit process. In the next couple lessons, we're going to get some other tools to do a derivative or to take a derivative. For now, we have to do the traditional approach to this, okay? Which means the derivative, f prime of x, is going to be equal to the limit as delta x approaches 0. Now, people have a tendency to forget about that limit, but remember, without the limit, you're just calculating a secant slope. We want the slope of the tangent line. X plus delta x quantity cubed plus 2 times x plus delta x minus bracket, that was supposed to be a bracket, x cubed plus 2x all over delta x. Without going any further, you see how much fun, that was sarcasm, this would be. Because now I have to take a binomial and cube it. Squaring binomials is bad enough, but now I have to cube a binomial. Then I have to distribute the 2 to these. Then I have to distribute the minus sign. Then factor out a delta x and cancel. It gets to be tedious, time-consuming, and we need a different way to do that. And that's what we're going to do in the next couple days. Just for giggles, how would you do that? Anybody?
I usually just square it and then multiply it by x plus changing the x again.
Okay, so you just grind it out. X plus delta x times x plus delta x plus x plus delta x.
Yeah.
Nothing wrong with that. Anybody have a different technique? I'm looking to see if anybody knows that thing, or if you learned that thing.
Is it x plus delta x and then times x squared? I forgot if it's minus or plus.
Plus.
And then plus, okay, plus x times delta x minus delta x squared.
No, you're factoring. We want to multiply it out.
Oh, okay.
Did you again with the Rona going on? Did you guys learn Pascal's triangle?
Yes.
Do you remember Pascal's triangle? You
I
could.
don't, but I don't
Okay, but you know what it is. You could use Pascal's triangle too. I, however, would do exactly what Max said, is I would multiply that beast out. So I would get x plus delta x times x squared plus 2x delta x plus delta x squared minus 2x plus 2 delta x minus x cubed minus 2x all over delta x. And you can see how much fun this is. Oops, this should be in parentheses. That's sloppy there. So x cubed plus 2x squared delta x plus x delta x squared plus x squared delta x plus 2x delta x squared plus delta x cubed minus 2x plus 2 delta x minus x cubed minus 2x. I just screwed everything up over delta x. Okay. My point being, this is becoming a major problem here. I've got a whole bunch of mess going on there. If I did it right, though, I should get some canceling. Yeah, this 2x would cancel with the 2x I had back there that you can't see. The negative x cubed cancels with the negative x cubed there. I think everything else has a delta x in it, which gets me to the limit as delta x approaches 0 of... Okay, so everything gets a delta x canceled out of it. That one goes away, one of those goes away, that goes away, one of those goes away, this becomes a 2, and that goes away. So I think I'm left with 2x squared plus x delta x plus x squared plus 2x delta x plus delta x squared. Yeah, I screwed up somewhere. I know I screwed up because I know what I'm supposed to get for an answer and I don't know where I made my mistake.
I think you made the 2x negative, if I'm not mistaken.
Yeah, it should. I got the negative 2x from there and then the positive 2x canceled. That's 3x squared. That goes away. That goes away. I screwed up somewhere. What I should get for an answer is 3x squared plus 2. Okay, because this would combine with this to give me 3x squared. This would go away to 0. This would go away to 0. This would go away to 0. So I'm missing this 2 that I know I'm supposed to have. Now, how do I know I'm supposed to have a 2 there? Because I know where we're going and I know how to quickly take a derivative. So what's my point? My point is, A, I make mistakes too. B, this is a pain in the butt. And C, we'll learn a quicker method to do this that doesn't involve this limit process.
didn't carry the 2 throughout the problem.
Which two?
One from this, I don't know, there was one at the start.
Oh, so we're just going to go, okay. You're right. Yeah, I missed that too. Yeah, okay, there it is. It magically appeared. There's the correct answer. Awesome. Thanks for the cover, Dylan. That's good. I like that. All right, so differentiability and continuity. Let's take a look at this. It's an absolute value graph. Is that graph continuous? Yeah.
Yes.
Yeah. Oh, okay. So we could do the formal definition, but I'm tired of that. Simply put, yes, because I can draw that V without picking up my pen. Beautiful. Can I take the derivative? So we want to talk about continuity versus differentiability. If I pick a point over here, what's the derivative over there? Well, it tells you. It's right there. The slope of any tangent line to a line would be the slope of that line. Can I take the derivative over there? Yeah, it's right there. But what about that guy? What's the tangent line look there? Well, you might say, oh, that's 0 because it looks like this. Okay. Well, what if I do this? What if I angle it a little bit more? Does that also work? And I could angle it a little bit more like that. There's a lot of different ways that I can hit that point. The idea being is that that point is a point of non-differentiability, commonly called a corner. Okay. We cannot take the derivative at 2 for this particular function. And that's going to happen a lot. Okay, so we did that already. We talked at the slope at the left and the right-hand side. And so we get to this idea. If a function is differentiable, in other words, if you can take the derivative everywhere, then it has to be continuous. Okay. Differentiability implies continuity. However, the opposite is not true. Continuity does not imply differentiability. For those of you that had me for geometry, you remember we spent a lot of time talking about dogs and golden retrievers. All golden retrievers are dogs, but not all dogs are golden retrievers. The same is true here. Okay. If you can take the derivative, it has to be continuous. However, just because it is continuous doesn't mean it's differentiable. Technically speaking, we call that a non-reversible statement. I have a wife, therefore I'm married. The reverse of that is not true. If I'm married, I have a wife, doesn't necessarily need to be true. I could have a husband or, you know what I mean? So that reversibility thing there. Okay? We're all done. So this is just dipping our toe into this insanity that is derivatives. And we're going to spend a lot of time on this. Very little time on what we've talked about here with this limit definition. This is more conceptual. Yes, the problem is ugly. You can see I screwed up on that cubic. But eventually, probably as early as Wednesday or Friday, we're going to throw this out and start looking at easier ways to find those derivatives. If, for instance, you come back to this thing where I screwed up, I knew by just looking at this how to find the derivative, and it takes about 3 seconds. It doesn't involve any of this limit process. And so from this point on, after we get done with this limit stuff, my goal is to just give you more and more tools to take derivatives, to present you with weirder and weirder problems to see if you can find the derivative. Okay, using the tools that I give you. Okay, so we got things like the power rule, the quotient rule, the product rule, the sum rule, the difference rule, chain rule. All these other things are going to start coming into play.